Okay, so a big welcome back to everybody. Hopefully we've got a few people who are visiting for their second, third, fourth, fifth, however many times you've been in the webinars, or maybe we've also got some newcomers. A big welcome to everybody. Either way, the Resources Conservation and Recycling webinar program. I'm your host, Mitchell Jones. I'm the outreach editor at Resources Conservation and Recycling. And I will be your host for today and for the future as well, for now at least. So a big welcome. This is our English language webinar program. It's run every second Thursday at 10 o'clock a.m. Pacific Standard Time. The webinar program basically comprises articles that are selected. We have two selected articles for each issue, and the speakers of those articles are invited to present their article to you in this format that we are currently enjoying today. So you can expect a broad scope. You can expect all kinds of articles. Basically anything that we publish, you might see here. Our emphasis is on an accessibility focused program. So we do ask our speakers to avoid too much field-specific terminology or to explain fundamentals prior to going into more complicated details so that everybody can enjoy the webinar in the best way possible. And so far, we've had I think a fair bit of success in our great speakers really doing that. So a big thank you to our previous speakers also. So registration is necessary for these webinars. If you don't know yet how to register, the registration links are circulated in the Resources Conservation and Recycling newsletter, which is sent out at the end of the month. It's also, all the links are also available on our Twitter, Facebook, and LinkedIn pages if you need them. They're right there. Alternatively, if you would prefer to watch the live stream on YouTube, that's also available. You can also access all of our archived content, so any previous webinars, all available at youtube.com/@RCR journal. The final point is we've been getting some really great feedback from a lot of people and a large amount of feedback. So I want to thank everybody for providing feedback. We do really appreciate it. We take it seriously. We do use it to make changes to our program. You will also have the opportunity to provide feedback at the end of this webinar. If you do have the opportunity or the chance to do that, it's greatly appreciated. You'll get the survey link automatically at the end of the program. So then I will touch on our program for today. So before I introduce our speaker. So for those that maybe are new, not read mode, full screen mode. For those of you that are maybe new today, we have the same event program each time, but I will touch on the fundamentals. We have the welcome address, which you've just received. We have the introduction to the journal, which I'll give you in a moment. And I'm going to also introduce our speaker for today, Yi. Thank you, Yi, for coming. And then touch on basically how things are going to operate today in terms of interacting with the speaker and so on. Then we're going to have a 20-minute presentation, followed by 10 minutes of question time, and then a few closing remarks and some information on the next event. Yi has indicated he might need a little longer than 20 minutes. So we don't mind that, no problem, Yi. If you need a bit more than 20 minutes, that's fine. In terms of our journal scope, journal information, Resources Conservation and Recycling. I always say the clue's in the name. It is fairly clear what we're interested in. But just in terms of specifics, we are really interested in systems-wide strategies, technological, economic, institutional, and policy focus, resource management practices, conservation, recycling, and resource substitution, resource productivity improvement, restructuring of production and consumption profiles, and transformation of industry. So as always, if you have great research in those areas, be sure to submit it to Resources Conservation and Recycling. So the operational procedures today, please all communication in English. This is our English language program, so we do want it to be accessible to everybody, and we do use English as a bridging language. We also have Chinese language webinars if you prefer a Chinese language webinar. But today is in English, so please all communication in English. We have closed captions available for anyone who is interested. For people who might want to watch the webinar on mute while doing something else or any other reason, we have closed captions enabled. They're there if you'd like to use them. If you have any questions, please post them in the Q&A during the presentation. We will go through those questions in order of popularity. So if you see a question there that you would have asked yourself or that you find particularly interesting, be sure to upvote it, and we will be sure to address that question first. If you want to ask your question directly to the speaker, you can do so. All you need to do is raise your hand using the raised hand reaction. And if we have time at the end of the question session, you will be able to do that. Right, so then I will introduce our speaker for today. So today we have Yi BAO from Stevens Institute of Technology in New Jersey. Thank you for coming today, Yi. He's going to be speaking with us on the topic of AI-assisted design of low-carbon, cost-effective concrete. So Yi BAO is an assistant professor in the Department of Civil, Environmental, and Ocean Engineering and the director of the Smart Infrastructure Laboratory at Stevens Institute of Technology. His research interests include innovative materials, sensors, structures, robots, and machine learning for improving the sustainability, resilience, and intelligence of civil infrastructure. Before joining Stevens, he was a postdoc at the University of Michigan, Ann Arbor, and a guest researcher at the National Institute of Standards and Technology. He has authored more than 150 journal articles. Very nicely done there, Yi. That's a nice number. He received several research awards, such as the 2022 Best Paper Award from Engineering Structures. So without further ado, I will hand the floor to you, Yi. Thank you very much for your presentation.
Thank you very much, Mitch, for the very nice introduction. I appreciate it. Let me share my screen. Can you see my screen? Perfect. Okay. Hello, everyone. This is Yi BAO. It's a great honor to give this presentation on the webinar program of RCR Journal. And I really appreciate the journal and Dr. Jones for hosting this presentation. So my presentation topic is AI-assisted design of low-carbon, cost-effective concrete. This is a collaborative research between my group and Professor Weina Meng, who's my colleague at Stevens. All right, so this presentation as research actually was motivated by some NAE grant challenges for this century. The first challenge is about the aging infrastructure. So according to the ASCE's latest infrastructure report card, the rating is C-, which is a slight improvement compared to the previous rating, which was D+. C- still means pretty poor conditions, and such poor infrastructure condition adversely affects the safety, mobility, and economy. And the second grand challenge is climate change, which significantly magnify the challenge of aging infrastructure. And at the same time, climate change impacts the problems were aggravated by the civil infrastructure construction and repair activities. So for example, the cement production is responsible for about 7% of the global emission. And cement is essentially a very important component of concrete. So this kind of aggravates climate change problems. The third grand challenge is about clean water. The landfill of different types of waste, for example, the construction waste such as waste concretes, those could pollute underground water. So these grand challenges converge to the idea of utilizing waste to produce green concrete to have high performance and at the same time with high sustainability. So it's not new to use waste in producing concrete. Different types of waste have been used, such as industrial byproducts, municipal waste, construction and demolition waste. The different types of waste have been used to replace virgin ingredients of concrete fully or partially, such as the stones, Portland cement, and sand and other materials. And the waste materials have been used to produce not only normal concrete, but also advanced concretes, such as ultra-high performance concrete, engineered cementitious composites. So following the same idea, for example, fly ash and slag have been used to partially replace the Portland cement to produce engineered cementitious composites and also UHPC. And UHPC and ECC could achieve very high and unique mechanical properties, as well as the long-term durability. So it's very promising to use waste to produce advanced concrete, which can be later used for civil infrastructure. But there are some challenges. I will use the UHPC as an example, briefly talk about the design of UHPC blended with waste materials. The design of UHPC is often guided by the particle packing theory, which aims to maximize the particle packing density, aiming to achieve a very dense microstructure so that the material achieves very high mechanical strengths. But this theory is mainly used as a guide. In practice, we often use performance-based methods. So basically, we follow some steps to design the material gradually. So in each step, we fix some variables and just change one variable so that we can optimize the particular variable. Well, this method is very reliable, very robust, but the problem is this method is very labor intensive and very time consuming. Considering the curing of concrete, which usually takes at least 28 days, those experiments will take a long time. So it's very important to develop more efficient and effective methods to design concrete. So this research will focus on AI-assisted design or discovery of new concretes through a prediction optimization framework. This slide shows this framework. This framework is based on the integration of machine learning model, which is used to predict the concrete properties. And then this predictive model will be combined with the optimization algorithm to optimize the design. So the idea is that we use the available data, which is the source of knowledge, to we feed the data to the machine learning model. Then this model can be used to link the input information, which is concrete design variables, and output the concrete properties. So with this predictive model, we can perform optimization. The concept is similar to inverse analysis, so that we can set some target properties of concrete, and then we optimize the design of concrete. This research has been published in a recent journal paper in the Journal of RCR. So first, I would like to briefly explain the principle of using machine learning methods to predict concrete properties. Well, as we know, if we want to relate two variables, this is a very typical regression analysis. For example, if we want to build a relationship between the water to cement ratio of concrete to the concrete's compressive strength, we can plot the data points, and then we can perform the regression analysis to know the mathematical formula. Well, when we consider two variables, for example, if we add the sand to cement ratio, we can still perform a similar regression analysis, but this will be a 3D problem. Well, in practice, the design concrete is usually a high-dimensional problem. So we need the very powerful mathematical models, which is used to link the material design variables to the material properties. This is the role of the machine learning method here. And here are some example data we used to train the machine learning model. Those data were published in my collaborator, Professor Wina Meng's previous journal paper as an example. So you can see that we have the table including very detailed information of the materials and material properties so that we can build the correlation between them. Okay, the idea is pretty straightforward, but there are some important challenges. First, the challenge is related to data. Data is the source of knowledge. We use the data to train our machine learning model for the prediction. So there are some important questions. First, how can we efficiently collect the data and update the data sets? As you know, there are lots of data available in literature. How can we collect those data efficiently? And when new data becomes available, how can we update the data sets? Second question is how can we identify and remove anomalous data, because it's very common to have some errors in the data because of different reasons. And the other question is how can we select relevant variables from many variables, because there are so many variables. Another family or type of question is about machine learning models. As you know, there are many different types of machine learning models. How can we select or develop the most appropriate model for our particular problem? The next question is how can we optimize the concrete design by considering multiple design objectives? So this becomes a multi-objective optimization problem. And another very important challenge is about the variety of waste materials, because there are so many types of waste, such as fly ash, slag, waste concrete. And for each type of waste, there are lots of different physical and chemical variables. So this motivated our research. This slide shows the outline of this presentation. So I focus on introducing the AI Concrete Designer, which is integration of several technologies which are used to address the different types of challenges, such as the AI data collector, generator, processor, AI auto-learner, AI optimizer, and AI data presenter. I will briefly talk about each of those. First, I want to briefly talk about the AI data collector. The idea is to develop a AI technology that can automatically collect available data from published documents, such as journal papers, conference papers, and others. So we want to collect the very important data which will be used to train the machine learning model automatically. Well, a very important feature of this technology is that this method supports the automatic updation of the data sets, meaning when new papers are published, we can identify the new data in those papers. And why do we use the AI data collector? Well, obviously, this technology can help improve the efficiency and accuracy, because if we train a robust AI model, the AI model will perform consistently, will avoid the human errors, and the efficiency will be very impressive. Another important factor is the self-updatability of the AI model. Because of the self-updatability, we can enlarge, we can grow the data set, so we can grow the knowledge base of the AI model so that we can improve the accuracy, because we increase the data sets, right? We can increase the knowledge. As you can see from 2014 to 2022, the number of variables we can use in the design concrete, in the design of UHPC was increased. So this enabled us to consider new materials. So basically we enlarge the design space so that we can further reduce the cost and carbon footprint. Again, this slide shows how the accuracy increased over time because of the addition of new available data to train the machine learning model. And also the increase of the design space helped improve the sustainability factor of the concrete design. We can reduce the cost, we can reduce the carbon footprint over time because the increase of the data sets, increase of the design space. Okay. Then I want to briefly talk about the AI data generator. We have implemented the two main methods to generate new data. We call it generative AI. The first method is to use established theories or equations. And the second method is to use a so-called GAN method. So the concept is that we have some real data and we have another set of data with important features that we can combine the data with different features to enlarge our data sets. So as you can see, we have some test data, which is the real data. We use the test data to develop our GAN model, and then use the GAN model to help generate the AI data. And then we combine them together for larger data sets, including synthesized data and real data. The problem of data is that it's very common to have some anomalous data. There are different reasons that can cause anomalous data, such as errors in experiments, data entry, and data post-processing. So in our research, we developed methods to evaluate the features of the data so that we can identify anomalous data. As you can see in this figure, some data, they are very different from the majority of the data, right? In terms of some parameters. So we have considered different parameters. But the concept is that we identify the different features so that we can identify anomalous data. But the problem is that this method is based on data science. So it's possible that some of the data, some of the normal data are treated as anomalous data by mistake. For example, when you have a lot of sheep, and if you have some dogs mixed inside, sometimes it's not very accurate to identify which is dog, which is sheep, right? So we come up with a method to solve this problem. So basically, the data are ranked by their normalness based on the feature analysis. We can analyze data and then we rank them. So similarly, we can rank the dogs and sheep according to their appearance, as shown here. So basically, we define the contamination ratio. This ratio is the percentage of anomalous data in a data set. So for example, we rank the animals based on the identified appearance. So some of the objects are considered as sheep, and some of those are considered maybe dogs. So we define a ratio, we rank them, and then if we vary this ratio, we will achieve different errors. So we want to see the relationship between the contamination ratio and the error, so that we can optimize, we can minimize the error, right? So another problem is about the variable selection. There are so many design variables for concrete. So if we include too many variables, the machine learning model will be high dimensional. So it's very complex, and sometimes it generates inaccurate results. Well, on the other hand, if we do not include the necessary variables, also we are missing important factors, right? So the machine learning model will be inaccurate too. So in our research, we proposed the two criteria to select the appropriate variables. So the idea is that we want to make sure that the input variables are independent with each other. And there's also very strong correlation between input variables and output variables. So we can analyze their correlation, and then we can optimize the selection of the variables based on correlation analysis. Well, the next challenge is about the selection or the development of machine learning models. There are so many types of machine learning models. How can we select the best one? Or in other words, how can we develop the best machine learning model? So in our research, we developed AI auto learner, which can help us automatically select and optimize the machine learning model. So basically, we could combine different machine learning models so that we can achieve the most accurate results. So this slide shows that we compared our developed model with the existing state-of-the-art machine learning methods. We found out that our proposed method can achieve the most accurate results. As you can see, the predicted result is closest to the observed or the real data. Okay, so with that, we are able to do the prediction of the concrete properties based on the input variables, which are the concrete design variables. And then the next main step is to perform the optimization based on this prediction optimization framework. The problem for concrete design is really considered as a multi-objective optimization problem. So in this case, we consider some important concrete properties, such as the mechanical properties, ductility, durability. We also consider the fresh properties. Those properties in green color could be predicted by the machine learning model. And at the same time, when we define mixture design, we can also calculate the cost, material cost, the carbon footprint, and embodied energy according to the inventory. The inventory is available from literature. So with this, we are able to define our design problems. So basically, we can do the predictions using the machine learning model, and we define our design objectives, which could include the multiple objectives, and we can define our constraints, and then we perform the optimization. So we have implemented the advanced optimization algorithms in order to find the global optimal results instead of local optimal results. And here I provide a very simple example for the AI-assisted design of green UHPC. So in this case, we are able to use the following materials. So this is like our design space. Those materials are available for this development. And we set some design constraints, including the flowability and the 28-day compressive strength. Those are the two important factors to define UHPC. And then we define our design objectives. In this case, we wanted to minimize the material cost, minimize the carbon footprint, and maximize the compressive strength. Okay, so this shows the flow charts of the design task. And by performing the multi-objective optimization, and we use the TOPSIS method to select the results, we found that the optimal results designed by AI has very good performance in terms of the low cost, low carbon footprint, and very high compressive strength. In this case, you can see the compressive strength of our design UHPC is comparable to the state-of-the-art UHPC mixtures, and but at the same time, the cost and carbon footprints of our design UHPC are much lower than the reference sustainable or green UHPC mixtures. That means this method is pretty promising for concrete design, but we identify important limitation of this method. When we use this method, we define the materials, like waste materials, based on their names, such as fly ash, slag, waste glass. But this name is a pretty general name. It's not directly reflecting the physical and chemical variables. So because of this problem, the developed machine learning model could be very useful for a particular case, but it's hard to generalize the machine learning models for other cases. So in order to resolve this problem, we tried to develop methods to consider the physicochemical properties of our raw materials, such as fly ash. According to ASTM standard, the definition of class C, class F fly ash are based on big range. So if you are given flash, if you know this is a class F flash, well, the physical and chemical properties could vary in a significant range. So those names are like engineering names, not very informative for machine learning models, because they could have very different physical and chemical properties. So in order to consider the physical chemical properties, we created artificial language that can be used to describe the different types of waste materials in a more informative way. So this slide briefly shows the methodology. So compared with the current method for using machine learning model, which use the numerical data sets only. In this case, we propose a method to consider the chemical composition, the particle size distribution, curing time, and specimen geometries. And if needed, we can consider more different types of variables. We use the artificial language to describe the raw material, which could be waste material. And then we perform data mining to generate the numerical data sets. Then this numerical data sets could be used to develop our machine learning model for the property prediction, right? In this way, our machine learning model will be able to could be generalized for different cases. Whenever you know the physical chemical properties of certain waste material, we can feed the information into our machine learning model to do the prediction and optimization. Okay, this slide shows an example of the artificial language that I just mentioned. So basically, we use some symbols to represent different information. And those symbols could be assembled to generate sentence-like elements. So for example, for the curing time, we use this sentence-like expression. And finally, the sentence-like elements could be further assembled to generate a sequence of sentences. So for example, if you have a structure like ABC, S1, S2, Sn, we can express the sequence of sentences in this way. So our input information is not a single number anymore. It's a sentence. And output is the concerned property. In this case, that's the compressive strength. So we can generate a lot of data like this. And then we use this kind of data to generate the numerical data set, and then we use numerical data sets to do the machine learning model. So this slide shows that when we use this method, our machine learning model can achieve pretty nice accuracy. And as you can see, the performance metrics R square is pretty good. And another important or interesting thing of this technology is that we could use this method to investigate the physical and the chemical reactions. So if you perform the interaction analysis, this is the formula we defined to perform the interaction analysis of different variables, X and Y. So we can generate the interaction map in this way. The red color means the variables have very strong interactions. For example, if we look at this red square, we know this is aluminum oxide and calcium oxide. So that means probably there are some important reactions between aluminum oxide and calcium oxide because they have very strong interactions. And indeed, from simulated chemistry, we could confirm this assumption. So in other words, this technology enables us to consider the interactions between the different physical and chemical variables. And this gives us very important notifications about potential reactions. So for some reactions, maybe we didn't understand it very well, then we can perform further research to understand. This will generate new knowledge for materials. So briefly summarize the conclusions of this research. The machine learning-based prediction optimization framework can predict the key properties and optimize the design of green concrete. The developed AI data collector and AI data generator are very effective in producing and updating the data sets, which can be used to improve the performance of the AI models. The AI data processor can facilitate the data cleaning and variable selection. The AI auto learner enables automatic generation of machine learning models with high accuracy and high generalization performance. The AI optimizer can effectively perform the multi-objective optimization of concrete design. And finally, the artificial language or the AI data presenter can enable us to consider the physical and chemical properties of different solid wastes. This will enable us to facilitate the design of concrete with various types of waste materials and achieve high performance. And it's possible to use the proposed AI technology to further investigate physical and chemical reactions for new concrete systems. Here I show a list of references related to this presentation. And finally, I want to acknowledge our team. So this research, most of the research was performed by our PhD students, Mr. Majubi, Mr. Guo. Mr. Majubi recently graduated, so I should call Dr. Majubi. And this research has been funded by multiple external sponsors. I really appreciate their support. So also, I appreciate everyone's participation and your attention to my presentation. And this is my email address. So in case in the future you have any questions related to the presentation, please feel free to reach out to me. Thank you very much.
Thank you so much for that presentation, Yi. I really have to commend you there. You did an exceptionally good job at walking everybody through that step by step and providing all the background information, all the fundamentals, explaining everything very clearly, and then moving to what you actually did. I thought that was exceptionally good, and I'm sure that the audience will, well, for those people who it's a new topic, they will certainly have learned something from that. So a really nice presentation and also a really interesting research topic. I think it's quite crazy what we can achieve with AI and some of this in terms of design and accelerating this kind of progress. So that's very exciting. Thank you.
Thank you so much.
So we do have a few questions here. I will answer the first one briefly because it relates to the availability of this this presentation. So the question is, will this recording and/or slides be made available to us? So this recording is currently being live streamed on YouTube, and it will be archived to YouTube, the Resources Conservation and Recycling YouTube channel. It's youtube.com/@RCR Journal. You can see this the recording of this webinar at any point on that link. As for the actual slides, that's at the discretion of Yi. I'm sure you can email him and he will be able to tell you whether that's appropriate or not. So our second question, Yi, did you have any issue regarding the heterogeneity of concrete mixtures in different places of the world, e.g. cement types, specimen shape and type, unit conversions, or did you limit your AI data collector to only a few countries or regions?
Well, that's a very good question. Thanks for the question. Yes, indeed, we had this problem. So one of the challenges of using AI is the large significant scattering of data. We have lots of variables, and you have mentioned some important variables. Indeed, we considered some of those variables, and in the particular data that I presented, I think we kind of limited our screening space to I don't remember very clearly, but probably it's North America. So, but this method could be extended. If we collect more data, we can consider more variables into the machine learning model. So that in the future is promising to overcome some of the limitations currently we have.
We have another question here. What was the final size of your data set? How many instances were collected and how many were created?
This actually, the exact information was detailed in our journal paper. I don't remember this very clearly, but I think we consider the more than 1,000 data mixtures, which is relatively small compared to a lot of machine learning models. But it's possible to use a smaller data set if the machine learning model is pre-trained already. Use bigger data sets. So for the detailed numbers, maybe you could check our published journal paper for the details.
Very nice. The next question relates to your actual AI tool. So the question is, thank you for the great presentation. Do we have access to the tool you developed? I don't know if you want to comment on that or if that's something that the person should email you about.
I can briefly mention that. So currently, this tool is not made available for the public because they is still in the research stage. We want to further evaluate the performance rigorously. After we really test the performance, we gain more confidence, we will consider making it available for the public.
The next question, thank you for the awesome presentation. How did you choose data with respect to publications? How did you choose the model generator?
So let me try to understand this question better. We choose the data from publications. Currently we limit the data collection from tables. So we kind of identify some keywords, and we use the keywords to help search the publications. So we search the publications from several databases such as Science Direct and Google. So we use the keywords to find the publication, and then we use our AI methods to search the useful data from those publications. And then we can extract those data from the papers and then generate our data sets. And because this is automatic, we can perform this periodically so that we can identify the new papers, new data, and then use that to enlarge our data sets. Well, this is our data collection, but for the data generation, that will be a different story because the data generation is currently is not directly tied up with our data collector. So it's separate. We generate our real data sets, which is based on experiments, and then we use this to train our AI model to generate new data. So they are two different separate things, but eventually we plan to integrate them together to perform it in a closed loop.
Very nice. The next comment, very nice presentation with a big thumbs up for you.
Thank you.
My question, considering the potential variations in raw materials and construction practices across different regions, how adaptable is the AI-assisted design approach to different geographical contexts? Have you explored any strategies to address regional variations in the physicochemical properties of raw ingredients for concrete?
Well, that's an excellent question. Thank you for bringing it up. Actually, this is something we are trying to resolve at this time. We do see the large variations related to the regions in different parts of the world. We do have very different materials, and not only the materials, the physical and chemical properties, but also the inventory data is quite different. So for example, the cost for a certain type of material could be very different in different regions of the world. So I think it is possible to consider that, but we are working on it now. But I think the key is that we wanted to develop the capability to consider the physical and chemical variables, such as the chemical composition. If you have 2 benches of fly ash F, Well, their names are the same, but they have very different particle size and very different chemical compositions. So currently, we in our artificial language method, we try to address this problem by not considering the name, the engineering name, such as flash F or flash C or slag. We just focus on the chemical and physical properties, which are the real factors that affect the material properties at a later stage. So we try to build this correlation. But the capability or the performance of this method in different regions has not been fully tested. So this is something we welcome collaborations for future research.
Very nice. Congratulations, great job. What's the stage of the research today? There is some real application simulated using this method?
Well, that's a very good question. So this is still in the research stage. So we still have a lot of challenges to address. Today, I just briefly mentioned some of the challenges that we encountered a few years ago. But then as we do more, we find more challenges. There were some very good, very inspiring questions asked related to the performance and the availability. So indeed, I don't think this is ready for engineering for industrial applications yet. So for example, one of the challenges, one of the questions I was asked very often is that your method is based on data. Well, is it possible that your results violate some some established principles or laws from the perspective of physics or chemistry? Because our model is data-driven, it's not fully considering the physics and chemistry. So that's something we are working on. We have made some exciting progress. So if there's opportunity, I would be happy to share our progress in the future.
And the final question, Yi, which software of AI you use for data analysis?
So we have been using different softwares. So we usually write the code by ourselves using Python, and sometimes we use MATLAB. So there are lots of different platforms for you to nowadays. You have lots of tools actually for AI work. So yeah, if you have some particular interest, feel free to reach out to me. I can try my best to share the appropriate tools to you, because there are so many and it's related to your specific application.
We've had so much interest in your talk today. Perhaps you want to quickly note your email address again, Yi, just in case anyone does want to drop you an email.
Yes, let me share my screen again. So if you, yeah, this is my email address. And if you type my name in Google, you can probably find my contact as well.
Very nice. Thank you again so much for your presentation, Yi. It's obviously been very much appreciated. You can see that quite clearly. So I will cover a couple of closing remarks before we finish up for today. The next RCR webinar, which is Thursday week, at the same time, 10 o'clock Pacific Standard Time, will be presented by Kunyang Lee, who is coming to us from Imperial College London. Now, I'm expecting that to also be a very exciting presentation, so feel free to join then if you would be interested in hearing about simulating milk bottle recycling in the UK. So that's Thursday, July the 13th this year at 10 o'clock AM Pacific Standard Time. Be sure to join us then. Thank you again so much, Yi, for your presentation. I really found it exceptionally interesting, and it's very clear that a lot of other people also did. So thank you very much.
Thank you, Dr. Jones, and also I want to thank our audience for all of those very good, very inspiring questions. I really enjoyed the discussions with you.
Absolutely. Wonderful. Then thank you to everybody for coming. Thank you to Yi. And until next time, goodbye.
Thank you for the opportunity. Have a good day.
Goodbye.